Section 1.6 is all about valid arguments. And it's important to recognize that when we say arguments, we're not really talking about the kind of argument you have with your parents or with your friends. An argument is a sequence of statements. All of the things that are presented are premises. And from those premises, you get the conclusion. Essentially, we presume number one, and then presume number two, and then presume number 3, 4, 5, and then we conclude number 6 is true because of what we were able to do with the first 5. You're trying to take facts and show that you can put those facts together to synthesize another fact. Basically, I guess the example that's here are these 5 sentences, which we did, a week or so ago. And from these 5 sentences, you can synthesize the fact that this example is not easy. By the way, you may not have known that Lewis Carroll, who wrote Alice in Wonderland, was actually also a mathematician. I've mentioned before that mathematics was, up until a couple of hundred years ago, part of philosophy rather than part of science. And Lewis Carroll was a mathematician, a logician, and a minister, which was not all that unusual at the time. There are a couple of laws that you need to know about. One is called the law of detachment. I don't think it's necessary to know the Latin name for it, but you're certainly welcome. Modus ponens. There is a form of argument that is always valid. What we know about if-then statements is that they are only false when the first part is true and the second part is false. Assuming that we know if P, then Q, and assuming we know that that is a true statement, we know that if P is true, Q has to be true. And that's what this says here. If I say to you, if it rains, I carry an umbrella. If I'm telling the truth, the next time it rains, I'll have an umbrella with me. Here's how you would do a truth table for that. You notice that here you've got the if P, then Q is one of your statements, and you can use that in an and statement. This is true and this is true. That would be here, right? Then the conclusion Q has to be true. And here, the conclusion of a valid argument is called a valid conclusion. In other words, the truth of the premises guarantees the truth of the conclusion. You have to understand that a valid argument doesn't necessarily mean that it's true. The law of transitivity, it's almost like the transitive property. If P, then Q, if Q, then R, if both of those are true, then you could skip the Q altogether and just say, you know what? If P, then R. What does that mean? That's not a good one either. Let's just stick with the if it rains. That's pretty much what it is. If it rains, then I'll get wet. If I get wet, I'll catch a cold. That means if it rains, I'll catch a cold. Well, that's the law of transitivity. It says basically if you have 2 if-then statements and the conclusion of one is the same as the hypothesis of the other, you can slam them together and make one out of it. If P, then R. Okay. A proof of these different theorems can be done with a truth table. When you present the truth table, that serves as a proof. This one is modus tollens. I actually don't know what those mean. But basically, it's the law of indirect reasoning. And basically, modus tollens, Latin for method of denial. There you go. This one says, if P, then Q, and this says not Q, it means it can't be P. P can't be true. So in other words, again, going back, if P, then Q, if Q is false, in order for this sentence to be true, P has to also be false. So if P, then Q, not Q, then not P. Here are a couple of practice runs where they give you, actually this one here is the solution to the problem at the top of the section. Here, these are the covering the reading questions. Consider the following argument. For all integers n, if n is divisible by 3, then its square is divisible by 9. 10 is divisible by 3, therefore 10 squared is divisible by 9. The premises of this argument are the two statements. For all integers n, if n is divisible by 3, then its square is divisible by 9. So in other words, the universal statement is one of the premises. And then the other premise is 10 is divisible by 3. Identify the conclusion of the argument. Well, 10 squared is divisible by 9. That's the conclusion. Write the form of the argument. The form of this argument. Let's see, what do they mean exactly by the form? Well, these are the forms right here. Right. And this is the form we're talking about. Right. If P, then Q, in that case it was if it's divisible by 3, then the square is divisible by 9. And P is 10 is divisible by 3. And therefore, 10 squared is divisible by 9. So this is what that form would look like. Is the conclusion true? Well, no. 100 is not divisible by 9. Is the conclusion valid? Yes, the conclusion is valid because if the two statements were true, then the conclusion would have to be true. Let's just go back here so that you can see where that is. Right? Universal form has a similar property no matter what conditions are substituted in place of px and qx in the premises. The truth value of the form is true. Any form of argument having such a property is called valid, and modus ponens means method of affirming. True or false, the conclusion of a valid argument can be false. Well, we just showed that it can be. What a valid argument says is if the premises are true, the conclusion has to be true. Okay, a valid argument is valid regardless of whether or not the premises are true. Multiple choice, which of the following is valid by modus tollens? Okay, modus tollens. Now that was the one where we said if P then Q, and then we found out it was not Q, and so it had to be not P. That would be C, right? Let's just go back for a minute. Right, that's this one here. So it's kind of interesting that they would even ask that question because it really is exactly that. I guess the question here is, can you see it in terms of the notation? In 4 to 6, determine whether the argument is valid. Okay, if a person is at least 16 years old, then the person is eligible for a driver's license. So that's if P, then Q. Sarah is not eligible for a driver's license. So that's not Q. Sarah is not at least 16 years old. That's not P. And that's modus tollens, this one right here. Okay. For all real numbers x, if x is greater than 2, then x squared is greater than 4. For all real numbers x, if x squared is greater than 4, then 3x squared minus 9 is greater than 3. for all real numbers x, if x is greater than 2, then 3x squared minus 9 is greater than 3. What are we doing here? This is if p then q, if q then r, so if p then r. That's the law of transitivity. Okay. If Ken wants to see the world, then Ken will join the Navy. Ken wants to see the world, then Ken will join the Navy. If P, then Q. P, therefore Q. Okay. That's the law of, go back here, the law of detachment. If P, then Q. P, therefore Q. Which of the three puzzles of this lesson was not used in the resolution of the Lewis Carroll puzzle? Well, we actually didn't talk about that, so let's go back and look at it. If not G, then U. If G, then H. Not R. Well, let's start with that, because not R is the only one that's just not conditional. Not R. If not R, then not U. So we know, right, that not U must be the case. And if it's not U, then this one here, if not G, then U, we find out that it's not U. The law of indirect reasoning says this has to be not G, which is G. So we've used that one. And if G, then H, if we know that G is true, then H has to be true. Now, if H is true, we go back over here to the law of indirect reasoning. If E, then not H, but we know that H is true, so then this has to be not E, and that's what we're trying to conclude. So the one we didn't use here, we used indirect reasoning, we used the law of detachment, we did not use the law of transitivity. For none of these, the premise was the same as the conclusion of another. That's what you would need to put them together to make the law of transitivity. So that's the one we didn't use here. All right, what else here? Complete the proof of the law of transitivity. I don't think I'm going to do that here because I think they gave you the truth table. They're now telling you to just fill it out. That's something you should be able to do. Write the law of indirect reasoning using the symbols and prove the simple form of the law of indirect reasoning. For the law of indirect reasoning, if you write it using these symbols over here, and it should be pretty straightforward, so I'm going to leave that to you. If you have questions about it, please let me know.